we'll get the slideshow set up from the current slide. Okay. Now, remember we've talked about parametric equations. That's the title of this chapter. Parametric equation, polar coordinates, and conic sections. We're basically focusing on parametric equations. That's what 11.1 focused on. Okay. However, 11.2, arc length and speed, this is arcs that are described by parametric equations. If you're doing arc length of a function, you already know how to do that. We did that back in, what, Cal 2 probably? Somewhere back there. But now we're doing arc length for parametric functions. Okay, certainly this is not a function, y is a function of x, is it? No, fails vertical line test in many places. But this could be, and probably is, a parametric equation where y is some function of t and x is a function of t, and that produces this curve C, curve or pathway that is also a function of t. So here it would be at P0, which is C of T0, at P1, C of T1. So C is your parametric, is the curve function, which is a combination of the x and y's as a function of t. And the curve goes around here. Here's P2, C of T2, P3 of C of T3, P4, C of T4, and P5 of C of T5. Now, why 5? Well, because we're doing a polygonal approximation for the arc length of this curve. Well, the distance between P0 and P1 is that straight line distance. Obviously undershooting the arc length a fair amount, right? Then the next from P1 to P2, again, the polygon here undershoots the length of the actual curve. And again, P3, P4 is closer, P3 to P4 is closer, but still is less than the actual arc length, and then the P5 again undershoots. So, that is an approximation, maybe not a great approximation, but we can calculate that. We can calculate, if we know the x value and the y value here, the x value and the y value there, we can calculate the length there. Pythagorean theorem, basically. Delta x squared, delta y squared, okay? So we can come up with the blue lengths that would be a rough underestimate of what the pink length would be. But if you doubled the incidence, in other words, you make twice as many intervals between P0 and the end, which is Marcus here. So we're just missing Faith. And she sometimes, I think, is either at the Birmingham campus or somewhere. So she, I think, it's a little bit later coming in most of the time. Anyway, when you go to twice as many line segments to approximate that length, look how much closer you come. You've got 10 spaces here. P0 to P1, of course, is a shorter length, but it's a much better approximation to this than that is to that. Then P1 to P2, boy, that is a great approximation, and even better is P2 to P3. P3 to P4 is about like some of the others, but much better than anything here, pretty much, except maybe that one. And then P4 to P5 is pretty good. P5 to P6 is very good. P6 to P7 is excellent. P7 to P8 is very good. P8 to P9 is okay. And P9 to P10, very good. That approximation, which you get the same way you did before, you can calculate those lengths by the Pythagorean theorem of your delta x squared plus delta y squared gives you that squared. So, again, that approximation is going to undershoot, but come much closer. And of course, how would you get the actual length, or at least get closer and closer to it? smaller and smaller subintervals, right? So keep doing that. So guess what the limit of that delta t would be? A dt. In other words, you're doing the integral. And let's see what that integral would be. The distance between pi minus 1 and pi is the square root of the difference in the x values. Remember, expand this so you can see it a little bit better. Also, people at home probably can too. All right. So the segment between pi minus 1 and pi would be the square root of the difference in the x's squared plus the difference in the y squared. Pythagorean theorem, okay? This is a change of x's squared, change of y squared. That would be the length here from pi to pi minus 1 to pi, okay? Where each of these functions, x and y, are functions of your parametric equation, or functions of your independent variable t, okay? There's your polygonal approximation to the arc length, okay? And the closer that I and I minus 1 are to each other, the better that approximation is, okay? Now, they do some more manipulations with this, but then ultimately what they're going to do is sum all of those arc lengths together. Section lengths, I'll say it. They're not arc lengths yet. That's what we're approximating. So we're approximating those polygonal approximations. The pi minus 1 to pi, we're counting I from 1 to n. So the first one's going to be the length from p0 to p1. Add to that the length from p1 to p2. Add to that the length from p2 to p3, all the way up to pn minus 1 to pn. Sum all those together, and those merely the summation of I1 to n of. Now, how did they get from the previous step to this step? Let's go back and see. Okay? Now, I can't write on this unless I leave it small like that, so sorry, it's going to stay small. Okay? But here's what we're going to do. Let's take this one. I'm going to bring down my square root symbol a little bit further. And what I'm going to do is do a ti minus ti minus 1 squared. Over here also ti minus ti minus 1 squared. Okay? Now I've divided everything under the radical by ti minus ti minus 1 squared. I can't just do that unless I also multiply everything there by the square root of ti minus 1 squared. Which is, the square root of that thing squared is ti minus 1, right? Outside the radical. These are inside the radical, so this is the square root of the squares. The square root of the square is just that root. Okay? Now, what does that look like? Change of x divided by change of t. That looks like, especially as the ti minus 1 is getting smaller and smaller and smaller. That's dx dt. This is dy dt. Of course, this is dx dt squared. This is dy dt squared. And what is this? Your dt, right? So that then is how you go from this form to that form, okay? We're going to sum all those together, and what we're summing is x prime squared. Now, I don't like the way they've written this, okay? It's a bit abhorrent to me, okay? Because this looks like it's the ti prime is what's being squared. It's not. It's the x prime squared, Okay? So I like to put my square in there. Okay? Ew. Right when I'm trying to do something fairly delicate, it gives way on me and it makes a big blob. Okay, put my square there, not there. Put my square there, not there. But that's your delta t on the outside, delta t survives. Now, why did they do that? I don't know. If you're taking the limit and letting this go to y prime, let that go to dt. I mean, you have to take the limit as the delta t, which is in your denominator, is going to 0 to get that to be a y x prime and that to be a y prime. So if you're doing that, going to delta t, well, I think I see what I'm doing. And this is delta ti, but yeah, I guess it's okay to leave it like that. Because you're still technically doing a summation. But you've already approximated the differences as a derivative. So it seems like to me you could go on and do it all and then make this an integral. But that's the next step. That's where they're heading. And again, I don't like their notation here, but here is their theorem 1. The arc length, let C of t be your curve or your pathway as a function of the t, whatever that is, okay? And let this be defined as your x of t, y of t. That's a two-dimensional curve on a plane. The x of t is a function of t, the independent variable t. Y is a function of independent variable t. And then when you combine those x, y ordered pairs together, you get your pathway or your curve. Now, x of t, y of t, where both the derivative of each of these do exist, where x prime of t exists and where y prime of t exists. Okay? Not only do they need to exist, they also need to be continuous. The derivatives need to exist and be continuous. Like the two functions can't go like that. The derivatives are defined everywhere, but they are not continuous. Can't have that. You need something better. Then the arc length S for the curve C of t, pathway, from A to B, A less than t is less than or equal to B, is equal to the arc length. S stands for arc length. The integral from A to B of the square root of x prime squared of t. It's not, this isn't of t squared, okay? If you're doing it this way, I would like to put a bracket around that. X prime of t squared plus y prime of t squared. So obviously you're not squaring the t, so it's okay. But I think it's a lot neater to put x prime squared of t plus y prime squared of t dt, because you're squaring the derivative, nothing to do with the independent variable. Okay? And then your delta t from before becomes a dt here. That's the arc length formula. And it comes from Pythagorean theorem and extension of that, you might say. All right, I think we're ready now for example 1. Oh, one other little thing first. Let's say that you have a function y is equal to f of x. Okay? We've had those before, right? Now, what would be your pathway in this case? Your c of t would then be some t for your x, so x equal t, your y is going to be the f of t. So then your c of t would be x of t, comma, f of x of t. Okay? So, even a regular old function like that you want to use this formula for, parameterize it that way. You know, and that works just as well. Okay? But let's see what happens when you use this formula on it. Your S, your arc length, is then going to be the integral from A to B, just like before. T is going from A to B. The square root of, but your dx dt, in this case, that's dx over dx. I mean, that just winds up being 1. I mean, okay, let's do it this way. Yeah. Let's do it this way. X prime of t squared, I'm doing it too, I'm on hot, plus y prime of t squared, but your y prime of t is your f prime of t, f prime of x of t, let me put it that way, squared, okay? And then your dt. But this time, if you divide everything here by dx dt, divide this by dx dt, actually divide this by dx dt. Let's see if that is indeed true. That is the integral from, okay. Oh, sorry. The square root of this thing squared. And leave that on the outside. And then you have to change your variables here. We'll get to do that a little bit later. I don't know. They're not dividing. I was sorry about this. Well, I'll leave it AB for now. You may have to work with that. This would be 1 squared, because this is dx dt, okay, plus, and then this one becomes your I'm sorry, this is the y up here. And when you do this, this then gives you your f prime of t, okay, because it's the they sort of glaze over a few of the finer points, but this is what it comes out to be, this f prime squared of t, and then ultimately this is going to be your t dt over here too. They skipped a lot of steps. I tried to fill them in, probably didn't fill them in very well, but this is what you get from that. So with that said, let's do example 1. Okay, so I'm going to clear all this writing here. All right, and we're going to use this formula here. They call this equation 3. We're going to use that equation 3 to calculate the arc length of a circle of radius r. Guess what, team? We know the arc length of a circle. That's the circumference of a circle. Well, let's see what it gives us. Okay? Well, here's the parameterizations for any circle R. Your x parameterization is r cosine theta. Your y parameterization is equal to, developing sort of a bad headache here, I don't know why. R times the sine, of theta. Okay. Hurting right behind my eyes. Okay, There's your typical parameterization for a circle, including the one they're talking about here. A circle of radius r. Capital R is a constant in this problem. Theta, however, is not. That's your variable. Okay? All right, what we want to do is use this formula to do the arc length. Obviously, your independent variable is not t, but theta. Okay? Now, what you want to do here is this dx dt here squared is now going to be dx d theta up here. So this will be dx d theta is equal to what? Okay, a little louder. Okay, dr d theta. Remember, r is a constant. Leave that alone. Well, make it an r, not a p. All right. So you're taking the derivative with respect to theta. What does that give you? Negative sine theta. And d theta, we got the d theta down there. Okay. And your dy d theta is r times the cosine of theta. Okay? Now, in the form down here, you're squaring those. So let's take this thing and square it. This thing and square it. This thing and square it. That thing and square it. Okay? So your dx d theta squared is going to be dx d theta squared. Positive r squared sine squared theta. What is your derivative there? Okay. R squared. The derivative of cosine squared is, oh man. R squared, we've already taken derivative, sorry. R squared cosine squared theta. Okay. Okay. Let's do the integral. This is that squared, this is that squared. So your arc length S is going to be the integral from, now, what's your independent variable here? There it was t, what is it here? Theta, yeah. That's an ugly theta right there. It looks like a t, but that is a theta, okay, as in everywhere. Okay. So what's theta going to be if you are going to calculate the arc length of a circle? Where does your theta go as you go around the circle? 0 to 2 pi. So those are your limits on the integral of the independent variable theta, 0 to 2 pi. Sorry. All right. Then you're going to have the square root of your x prime squared, which is this thing, r squared sine squared theta, plus r squared cosine squared theta, and then we'll have our d theta. Okay, that's what your limits are on theta. All right, can you see anything you might do to that radical? Exactly. Factor out at r squared, but square root of r squared is r, so let's take that all the way out. It's just a constant. What are you left with? Okay, so it's going to be sine squared theta, square root of sine squared theta plus cosine squared theta. What is sine squared theta plus 1? Square root of 1 is 1 d theta. Hey, guess what this gives you? R times antiderivative of d theta would just be theta evaluated from 0 to 2 pi, and that's going to be, the 0 doesn't give us much of anything, so what you have is 2 pi r, which is the circumference of a circle, one time around, and that's exactly what we get. Okay, 2 pi r. Make sense? Okay, let's move on to example 2, and since they don't have room for this either, our slide. Any questions on this? Okay. Then let's just write on the same slide. Find the arc length of the curve given in parametric form by C of t is equal to t squared t cubed for theta okay. All right. For 0 is less than or equal to t is less than or equal to 1. Okay. All right. Now, there's a little bitty part of me, not very much, that says maybe we ought to graph that thing. Okay. Does anyone recall, well, let's just think about it. Where does it begin? T starts at 0. So what is it at 0? 0, 0. Okay? Now t is increasing from 0 to 1, so it's always staying positive. So let's just pick some value in between 0 and 1. A half. So that would be, so it starts at, let's just imagine that's the origin, 0, 0. So it starts there. And when t is 1/2, that would be 1/4 on x and 1/8 on y. So you really aren't going very far at all. But then you get around to 1 and you're at 1/1, which would be right here. So you're starting here and going up to there. So it's following a shape. It's not completely unlike a parabola, but it's not quite a parabola. Goodness gracious. I don't know why my eyes are doing this. I don't think it's that, but maybe 2 or 3 times in my life I've had my eyes sort of do blinky type things, and then I've gotten something close to a migraine. I'm hoping that's not it. It doesn't seem that bad, but it's just that it's hard to focus on anything. It's sort of like it's strobing a little bit, but I don't know. So anyway, that's the curve that you have here, okay? Whatever it's looking like there, okay? Now what we're asked to find is the arc length for this curve, okay? Here's the equation for it, but we got to do a few things first. By the way, the t squared is what? It's your x of t, and t cubed is your y of t. What do we have to do before we can calculate a arc length? Yes. X prime of t is going to be what then?
2t, and y prime of t, 3t squared, and faith is here. All right, perfect attendance. Way to go, team. Usually my Wednesday classes are pretty good about attendance. However, my morning class started with 0 students, then got 1, and then 2 and 3. So 3 out of 4 then. My second class showed up 3 out of 4, and now we got 4 out of 4. So way to go. I'll beat them all. Okay. And I got a paper in from this class, which is outstanding. Oops, what did I do with it? There. Make sure I keep it in here. Okay. That means half of this class is turned into papers before midterm. That's really good. Okay. So what's the next thing you've got to do? We took the derivatives, but what's the next one? You got to square those derivatives. And by the way, we're on example, goodness, where is it? Example 2 at the top of page 592. So your x prime squared of t is going to be what? 4t squared. And your y prime squared of t is going to be 9t to the 4th. Okay? I think we're ready to enter the formula now. The arc length S is going to be the integral. And what are we going from and to? 0 to 1 in t. Okay? The t's are going from 0 to 1. Not x's, not y's, but the t's. It's going to be the square root of 4t squared plus 9t to the 4th, and then you got your dt on the outside. Okay. Now, how would you proceed to try to do that integral?
Can you take the t squared out?
Yes, you can. Absolutely. You take a t squared out, so this is going to be the integral from 0 to 1, but you're integrating with respect to t, so you can't take it outside the integral, but you can't take it outside the radical. And the square root of t squared is t, and what you have left is 4t, actually just 4, because you're taking out t squared. Okay. Man. So, now, before we go any further, I was real tempted to go on and take out 4t squared and make it a 2t on the outside, and that would leave me just a 1 here, and then a 9 over 4, which is square root of that. You could do it, but I think we're okay doing this. And what do we have here? 9t squared dt. All right, how can you integrate that? Is there any way? Second? What'd you say? What's the suggestion? Ah, very good. Substitution. All right. Let u equal 4 plus 9t squared. Then du is equal to what? Goodness gracious. I'm sorry? 18, is that what you said?
Yes.
18t? Okay. 18t dt. Okay. All right. Now, I don't have an 18t dt in the original. I have a t dt. So what we need to do is probably divide out an 18. Okay. Now we're getting pretty close to it, I think. Whew, goodness gracious. The t dt, this part here is going to be du over 18. Okay, so I'm going to pull my 1/18 outside. Okay. And your integral is going to run now from 0 to 1. Well, let's see. We let u equal 4 plus 9t squared. So since we're changing to u du, let's find out what our limits are. When t was 0, what's u?
I have a question. When you take the t out, you take the t squared out or just the t?
Okay. What you're taking out here is a square root of t squared.
Yeah.
Square root of t squared is 2.
T.
All right. Is that the place you were meaning? Up there? Yeah. Okay. All right. So let's deal with the limits. When t is equal to 0, what's u equal to? 4. Well, 4 plus 9 times 0.
Yes.
So that's just 4. When t is equal to 1, what is u equal to? 13. All right, so you got new limits there. Now let's see what else we have here. We have this t dt, that's going to be du, and we already pulled the 1 over 18 out, so that's already out of our way there. Okay, and then we have square root of u, or u to the 1/2, right? That one I think we can do, right? Let's take the antiderivative of that, be 1 over 18. It's the antiderivative of u to the 1/2 du. U to the 3/2, but then you have to, I said 3/2 and wrote 3/3, that makes sense. Okay, but then I have to multiply by 2 and divide by 3. Okay, so the 2 will go into 18 9 times it. Okay. And we'll evaluate that from, from 4 to 13. Who wants to do that anyway? Okay, I can do the 4 part. The 13 really stinks. Okay. So this is going to wind up being the 9 and the 3, that makes 1 over 27. Okay, times that'll be 13 to the 3/2 power, whatever that is, minus, and I already took the 9 and the 3 out, so that's just going to be, what is 4 to the 3/2 power? Frankly, if I were you, I would take the square root of 4, which is, square root of 4 is 2. 2 cubed is 8. All right. Now that's, I can find, yeah, here we go. 1/27, 13 to the 3/2 power minus 8. They left the 4 to 3 halves power in there, but however, if you got your you got your calculator, 13 to the 3 halves power. Now, you know that's going to be something in between 3 and 4 squared. 3 squared is not 9, 4 squared is 16. So it's going to be something between 9 and 16, whatever that is. Use your calculator, see what it is. It's 13 to the 3 halves power. Okay.
46.8.
Okay, is that already with the minus 8? Or just the...
Oh, without taking minus 8.
Yeah.
So if
Yeah.
If you take the minus 8, it's going to be 38.
Okay. And then divide 27 into it. You get something close to 1 point, yeah, 4397. Approximately 1.4397. At least that's what they got in the book. And I think that's probably reasonable. Okay. So, that's the arc length of the curve going from 0, 0 up to 1, 1. Okay? As the t is going from 0 to 1, and your x squared and xt are, it's going up at some sort of a rate. And there would be the arc length. Okay. I think we beat that one to death. Let's go to this one. We talked about this shape before, but it's called a the length of one arch on the cycloid generated by a circle of radius 2. Okay? Here's the picture. Okay? Now, where this blue ball started, roll it back this way. This dot here was at the origin. As the ball begins to roll, the dot moves up in a fashion like this, okay? And up here, when t is equal to pi, when t is equal to pi, that's your parameter. When t is equal to pi, you have gone from, at this point, roll this back, your angle here is 0. Roll it around here, and you see that dot's going up, and when it reaches up here, it's maximum. Well, how far has that gone? From here to there, it's gone exactly pi. Spin of 1/2 of a circle. So that's pi. Now, your x displacement, on the other hand, has increased by 2 pi. Okay? Because when it's upright like this, somewhere else in here it's going to be exactly horizontal, and then somewhere else it's going to be, and when it's horizontal, it will be, this is also, let's phrase it this way. When your x value is here at 0, over here it's pi, over here it's 2 pi. I mean, it's the total length going from here to here, the time, what you traveled here is 1/2 of a turn, and in that half of a turn, you have gone the distance of a pi there. But your center has gone 2 pi because you see you've got motion also up this way, so this horizontal distance is actually a little bit more. And you can go back and check the formula for your cycloid, and you'll see that's the case. And then when it rolls off the rest of the way to the ground, it's 4 pi, but it's back here, 0 here. So the t over here is 2 pi, but the x value is 4 pi, and the y value with 0 to pi, and then back down to 0. If you go back and check the formulas, you'll see that is the case. Yeah, they did put them here too. So I was wondering why they didn't put them on the slide, but they didn't. Here were the. Well, I've got to reduce this. Okay. X is equal to 2 times t minus sine t. Your y value is 2 times 1 minus cosine t. Two times 1 minus cosine t, I thought it was. Okay. Those are the equations for the cycloid. And of course, then, when t is equal to 2 pi, t is equal to pi. Here, how far have you traveled? 2 pi minus sine of pi, which is 0. So that's why your x is 2 pi here. And your y value here is, when you travel t is equal to pi, this will be 1 minus cosine pi. What is cosine pi? Yeah, cosine pi would be minus 1. Okay, so 1 minus minus 1 would be 2. 2 times 2 is 4, and sure enough, your y value is 4 right there. So yeah, this is a cycloid, and you can see that here too. Here the the center of the circle is right here with the 2 down, and as it rolls along, the center is 2 from here, but by the time it gets here, this part is up right here, so you got 2 up and then 2 more up, that's a total of 4. So yeah, those are the equations for your cycloid. This is of radius 2. Remember they said this. A circle of radius 2. That's where these 2's are from. Otherwise these are R. So that is a fixed R. So our R here is 2. Okay. So that's where those come from. And your only variable is in your T or your angle, whichever you want to call it. Okay, they call it T. Okay, now what do you do with those? If you're looking for the length S of one arch of that cycloid, generated by a circle of radius R equal to, what's the first thing you're going to have to do? Same thing we did before. Take a derivative. X prime, this is of t now, is equal to what? Sorry. 2 cosine t, right? Okay. Or you could have done it 2 times 1 minus cosine t. It doesn't matter. I don't think it does. Okay. Your y prime of t is what? 2 times sine t. Okay? Excuse me. What's the next thing you've got to do? square each of those. X prime squared is then, I like it better, 2 times 1 minus cosine t. I mean, it just seems like it's going to be a little easier to do. What would that be? 4 times 2 cosine t cosine squared t. Okay? And your y prime squared four times what? Sine squared t? Okay, very good. Okay. And we want the arc length. So the arc length S is going to be the integral from t equal 0 to 2 pi. And it is your t that we're dealing with here, 0 to 2 pi. Okay, what goes inside the integral? The square root of your x prime squared, which is, okay, now notice is a 4 and a 4. Every term has a 4. So take out the square root of 4 and you get a 2. So let's put the 2 on the outside. Are you okay with that? Okay. Because the square root of 4 is a 2. Okay, so it just leaves what's in here. So here we have 1 minus 2 cosine t plus cosine t squared plus 16 yes, okay, I'm having trouble reading my writing here. Let me clean this up a little bit. Okay, I already took the 4 out. Sorry about that. Okay, let's go back. Okay, 1 minus 2 cosine t plus cosine squared t. That was what was getting hard to read. Plus, I already pulled the 4 out, so the square root of that, so that's out of there. And this is just a sine squared t, right? And then you got your dt on the outside. All right. What's some things you notice here? S is equal to 2 times the integral from 0 to 2 pi square root of 1 minus 2 cosine t yeah. But then sine squared plus cosine squared is another 1. And then you got a dt. Not under the radical, okay? So this s is now 2 times the integral from 0 to 2 pi of the square root of 2 minus cosine t. Whoops. 2 minus 2 cosine t dt. All right, now that does not look like a particularly inviting integral, okay? Yeah, number one, you could take out the square root of 2 to pull it out with the other 2 that you have, and that's one way to go. Let's see if the table at the back, way back, your integration, if we have anything that looks somewhat like that. All right. Looks like to me forms involving a squared minus u squared. No, that's not it. I think we'd have to do a substitution. I don't think that would quite be it. Well, okay. Now, they kept some things on the inside. I don't think it really, goodness gracious, it really matters that much about. They get their integral, and now we factor out the 4, but they basically have the x prime squared plus y prime squared is equal 8 minus 8 cosine t. Same thing we got, okay? Now, they're using an identity, and that's why I was surprised it wasn't in the back somewhere. I can't believe they don't have it in here, because it is a fairly common one. You look one more time. I'm having trouble focusing my eyes on it, but no, I sure don't see them. Just thought maybe I had missed them before, but I don't see. Sorry. Okay, but if you'll sorry, you'll notice in the margin there underneath the figure that's there, I don't think they have it on the slide set. They have this as from the half angle formula, I'm pretty sure. Okay? It's this one. That 1 minus cosine t, and it's not that hard to derive, but I'm not going to do it now, that this is exactly sine squared of t over 2. Okay? Now, what we have, if you factor out a root 2 out of this, you have exactly the numerator. Okay? So you can factor out a root 2. You have the numerator there. So let's do that. So we'll factor out a root 2. So this will be 2 root 2 integral from 0 to 2 pi of the square root of 1 minus cosine t. Okay? Now, according to this, 1 minus cosine t is 2 times the sine squared t over 2. So this would then be another 2, because of that one going over there. Sorry. 1 minus would be 2. So this gives you 4 times the square root of 2. the integral from 0 to 2 pi of sine squared t over 2. I've been leaving off my t's, but they've always been in there. Okay. Now,
What about the square root?
the what?
The square root.
Oh, yeah, you're right. And sorry, good point. Yeah, let's see. So I can't take, no, I think I can. No, not quite. Okay. 1 minus cosine t is equal to 2 sine squared t over 2. This was ugly writing, so I wanted to write it again. So that is what's under the square root. So the square root of this would be the square root of that. So I did take out too quickly. No, I think I'm okay. Let's go back. Okay. This was a 2 root 2 here. 1 minus that would be the square root of this. So if we take another this square root of 2 out front here, mixed with this one, this gives us the 4. Not 4 root 2, but just 4. Okay. And this then would be the square root of that, which is just be the antiderivative of sine, because we had a sine squared. Square root of sine squared is sine. Okay. Square root of 2 came out front. So, what is the antiderivative? I'm sorry. I can't talk, I can't write. I can't erase. Okay. All right. Let's clean this up some. That's a 4, I think. Okay. 4. Now, antiderivative of sine t over 2. That's going to be what? Antiderivative of sine is negative cosine, isn't it? Okay. T over 2, but then we got a 1 over 1/2, right? So that's going to be another 2. So that's going to be an 8 here. Okay? And you're going to evaluate this from 0 to 2 pi. Okay? Yeah. All right. So this is going to be an 8. And then what do we have here? Minus the cosine of pi, because 2 pi is going to be your t. So what is cosine of pi? -1. And negative of -1 is going to be 1. All right? Minus the cosine of 0. What's cosine of 0? 1. Okay? But you got a minus, which is plus, so it's plus another 1. So I get 16. Okay? Just seems like we keep multiplying by 2's. Yeah, sure enough, that's what they get. 16. Okay. I know that was long and circuitous, but I hope you do remember how you got that. And I just can't believe they didn't have that in the back of the book, because that's a pretty common thing. Well, I know it's back there, but just not in the integrals. If you go to the back of the book, before the integrals, before the differentiation, before the exponential and logarithmic, the elementary functions Well, don't tell me they don't have the trig function. Oh, no, they have inverse trig. They don't have the trig functions back here. I thought for sure they did. Oh, there they, no. Where do you see them? Oh, it's in the front. Okay. That's where the next place I was going to look. Yeah. The algebra, geometry, then the next page, trig. And there you see your, I believe it's called the half angle formula, double angle formula. Okay. Actually, you get the half angle from the double angle, but you see what we had here was sine squared x. What they have in the book, sine squared x is 1 minus cosine 2x over 2. If you then do t is 2x, then you have 1 minus cosine t over 2 is equal to sine. If t is equal to 2x, x is equal to t over 2. So that's where you get your sine squared t over 2, and then multiply both sides. Yeah. So they didn't show it in the integration, but they did show it in the front on that one. Okay. And then after that, it works out. And that's why, by the way, cycloids are such interesting phenomena. Because here you did all this, t was going from 0 to 2 pi, and your angles going there and stuff, and it wound up just a whole number. In fact, a very reasonable whole number. No decimals and fractions or radicals or anything else, just an integer, 16. Maybe part of that was because of what they use as the radius of the circle, but still, it wasn't anything too fancy. But anyway, it came out exactly 16. All right, let's move from there. It says, now consider, I think I'll just turn the page here and start writing on this one. Now consider a particle moving along a path c of t. This is kind of the bottom third of page 592, I think it is. I'm having trouble focusing my eyes. Following along a path c of t. The distance traveled by the particle over the time interval t0 to t is given by the arc length integral. Okay, so s of t is the integral from t0 to t. Now, notice what they've done here. You're saying c is a function of t. Well, that's your parameter. S is also a function of that t because you see you're going from some fixed point to some variable point. So that's going to be a function of this variable t. But as soon as you fix this to be a t, you can't have t's in here because that really gets too confusing. So they came up with a dummy variable. Theirs happened to be u. I'm saying you're a dummy. No, I didn't say that. That's beside the point here. It's some dummy variable. It didn't have to be u, but they just chose that. So that's fine. So your arc length formula is the square root of, remember it was x of t, x prime of t squared. Only it's no longer t, it's u. Okay, sorry, I just went through all that. Plus y prime squared of u du. But you see the du's are going from t0 to t. So the u is just sort of a dummy variable that's put in place here. So that would be a particle moving along a curve, a parametric curve, c of t, where c of t is x of t, y of t. Okay, just like we're used to. On the other hand, speed is defined as the rate of change of distance traveled with respect to time. So by the fundamental theorem of calculus, speed and this is where things get a little funny, because sometimes we use S to represent speed, especially in physics. The S here is representing arc length, so don't let it be speed. So the word speed, okay, is ds dt. Okay, your ds dt, but S is an integral with respect to t. So basically, what happens here, the derivative here undoes the integral, so to speak, and leaves you with well, okay, I'll write it the way they did. It is ds dt. In fact, I think I'll leave that in. ds dt, which is d by dt of this s of t, which is the integral from t0 to t of the square root of x prime squared of u plus y prime squared of u du, okay? But the integral undoes the derivative there, and since this is a t up here, we just plug it in there, so now the speed is equal to the square root of x prime squared of t plus y prime squared of t. Okay. Yeah. Which is exactly what they give here. Okay, so I'm going to blow this up. We've just derived what they came up with here. The speed along a parameterized path, the speed along a curve, c of t, where c of t is x of t, y of t. Don't like the wording here. I would say the speed along c of t, along that path, along that curve. This makes it sound like the curve is moving at a speed. It really isn't. It's the speed of the progression along that curve of x of t, y of t would then be ds dt, but s is an integral with respect to t. Okay, so this is just this. The square root of your x component of the speed squared plus the y component of the speed squared, which somehow feels very reasonable, doesn't it? That this is the x component of the velocity squared, but in the y component of the velocity squared, you square the squares of those and take the square root of it, and you get the ds dt. That really does feel like that ought to be right, and it is, okay? So, now, the next example illustrates the difference between distance traveled along a path and displacement, which is the net change in position. The displacement along a path is the distance between the initial point C of t0 and the endpoint C of t1. The distance traveled is always greater than the displacement unless the particle happens to move in a straight line. Okay? And here's the figure that illustrates that. Okay? Now, if you're going from this point to that point, if you're following some curve, pathway, C of t, it can go anywhere. This one has you going like this. Certainly the distance traveled is much further than your displacement. Your displacement is from your original to your final position, shortest distance, straight line. So the only way that your actual distance is going to be the same as that is if you are moving in a straight line. Any other way you're moving, you're going a greater distance than you would for a straight line. So the distance along a path is greater than or equal to the displacement. Always. Okay? Let's get a little more weird with it. Let's just imagine this point came back and closed the loop. your displacement now would be 0. But your distance would be that total distance wherever it is along that path. Non-zero. In fact, the distance between any 2 points along any path other than just sitting where you are is always going to be greater than or equal to the displacement. All right. Now, that leads to example 4, I hope. Okay? I think this may be example 4. A particle travels along a path, C of t is equal to, blow it up, at least for now, as soon as I go to right. Goodness gracious, I can't focus. Particle travels along a path, C of t. No, I can't write on it. There it is, right there. The hand is pointing at it here. Okay, there it is right there. You see the hand? Yeah, okay. That's your C of t. Okay, 2t, comma, 1 plus t to the 3/2. Okay? The first thing that it asks for is the particle speed at t equal 1. We'll assume units of meters in seconds. No, meters in minutes. Wow. Okay. So what is the particle speed at t equal 1? We'll assume that's 1 minute. Okay. All right. Well, from the previous thing, the speed is, well, you tell me. Speed, what is it in your parameterized equation? Square root of x prime squared plus y prime squared. Okay, I've really shorthanded it a lot. So what's the first thing you're going to need to do? One thing you're going to need to do. First, let's identify your x. X is equal to x of t is equal to 2t, and y of t is equal to 1 plus t to the 3/2. I hope I'm reading that right. I think so. What's the first thing you're going to have to do? Take a derivative. X prime of t is equal to what? 2 for 2. Okay. Y prime of t is equal to 3/2 t to the second 1/2. Yeah, okay. I thought you just said 1. Okay, what's the next thing we got to do? Square that. Pretty easy for the x prime. 4. Y prime squared is equal to what? 9/4 t. Okay, back to t again. All right, so your speed then is simply going to be the square root of 4 plus 9/4 t. All right. And when t is equal to 1, that's what it's asking for. What is the particle speed at t equal 1? So the speed at t equal 1 would be the square root of 4 plus 9/4. Okay, let's see if we can clean that up a little bit. That would be the square root of, we need both of these in terms of fourths. What would that be? 16/4 plus 9/4 would be, second, 25/4. What's the square root of 25/4? 5/2. Okay? So that would be meters per minute. Okay? Well, that's what they told us to measure in. 5/2 or 2.5 meters per minute. Good. So that's the A part. The B part, the distance traveled S, that's the arc length passed over, and the displacement D during the interval 0 to 4. Not 0 to 1, but 0 to 4. So, yeah. Let's do the arc length first. We've already got most of the pieces we need for this. Okay, and what is this going to be? The integral from 0 to 4 of, ugly looking square root sign. What goes in there? Same thing we just had, 4 plus 9/4 t, then a dt, right? Let's see, yeah, I believe that's right. Same thing that we had before, we're just integrating. All right, now, I think, again, not a bad idea to get least common denominator. So this is going to be 16/4. Factor out a square root of 1/4 and you get a 1/2. So let's pull that all the way out. So ST is equal to 1/2 the integral from 0 to 4 of square root of 16 plus 9t. dt. All right. How do you approach that? Okay, what do you want to substitute? I think that will work, but let's see what we do. Let u equal what? 16 plus 9t? Okay, then du is equal to 9 dt. Okay? But we don't want really what 9 dt is, we want dt, so dt is du over 9. If I could write, okay. All right, now we go up here, and this is 1/2. The integral, okay, we got to change our limits now, don't we? From what? I can't hear. Yeah, okay. You want to take the 1/9 out too. That's fine. So it'll be 1/18. Okay, got it. But what are our limits now? What's that? When t is 0, the u is 16. And when t is 4, 36. What is that, 52? Am I doing it right? 4 times 9 is 36 plus 16. I think it's 52, isn't it? Okay. Ooh, okay. What's your integral now? It's u to the 1/2 du, because I already pulled out the 1/9 because you wanted me to. And that'll be that. What does that integrate to? 1/18. I'll bring that down. Say again? Is it 42? Okay. 4 times 9 is 36, right? Plus 16. Yeah. Okay. All right. What does that integrate as? u to the integrate.
Oh,
3/2, and we'll have a 2/3, so let's put the 2 up top and the 3 in the bottom. That will be, it seems like we've had this before, if 1/27. How does this keep showing up? Okay, and this will then be, we're going to evaluate that from 16 to 52. What's that? Oh, we okay? All right. So if I'm not mistaken, this will be the square root of 52. Well, square root of 52, 52 is 4 times 13, right? Y'all aren't card players, are you? Okay. There's 52 cards in a deck of cards. That means 13 in each suit, right? 13 times 4 is 52. Okay? All right. So that would be it'll be an 8 here, okay, and then it's the square root of 13 cubed, okay, minus, I can do this one, the square root of 16 is 4, 4 cubed is 64, okay. Yep, and they do get something that's pretty much, yep, that's exactly what they get. They factor in 8 out of both of those and get 8/27 times the square root of 13 cubed minus 8. Okay, and they say that is about 11.52. You got it? Okay, 11.52. All right, so that's the distance traveled, S. And we want to compare that with the displacement, D, over that time interval. How do we get the displacement, D, over that time interval? Any ideas on that one? Oh, we're almost out of time. How can that be? Huh? Yes, you just plug in. You plug in S at 4, and that would be I don't know if you, let's call it C at 4. C at 4, you would be at the place 8. 1, okay. 4 to the 3/2 would be 8, plus 1 is 9. Okay. So that's where you were at 4. At 0, C at 0, you're going to be at 0, 1. Okay. So how far are you displaced there?
so we've got that value into which?
I think it works well if you plug it into this. Okay? And that will give you, C of 4 would be 8, comma, 1 plus 8, which is 9. I hope I'm doing that right. Do it in my head. The square root of 8 is, I'm sorry. The square root of 4 is 2. 2 cubed is 8, so that's 9. And down here it's 0, 1. Okay? So how far have you traveled? Well, the distance formula between those 2 points is the square root of 8 squared plus 8 squared, right? Which is the square root of 2 times 64, which would be 8 root 2. And if you do 8 root 2, that's about 11.31, which is very close to what we got on the other, which was 11.52. So you see, but if you look at this, I wasn't trusting this, but sure enough, here is at 0, 1, and here it is at 8, 9. Here's your displacement, the red line, the pathway that we calculated here gave us that. Not a lot of difference, but the distance is always a little bit greater. All right. I think we are awfully close to being out of time, right? Yes, we are. Okay, we are going to pick up in that right in the middle of page 593. In physics, we often describe, so we will start there next time. We almost finished 11.2. I mean, we came so close to getting this done. Homework exercises, do any of the odds 1 through 9? No, I'm sorry, 1 through what? No, okay. It says in exercises 1 through 10, do thus and so, and then right before 9 it says, and 9 and 10 use this. So any of the odds 1 through 7, and then do number 9. I'll put it that way. And then any of the odds, either 11 or 13, or both if you choose, and any of the odds 15 to 19. And then try any of the odds 21 through 29. I have a little new definition there, but I'll let you figure that out. Let's see. We haven't done surface area yet. We'll pick that up next time. So stop at 29. Okay. We'll pick up the rest of those later. Okay. Now, this is all we're going to do in chapter 11. When we finish surface area, angular velocity and surface area. When we get those two done, then I'll have your test ready. Knock on wood. Okay, I've got a bunch of things to do between now and Wednesday, but I'm hoping that I'll have some time this afternoon. Won't have much time tomorrow. I have a little bit of time tomorrow. But hopefully between those two times I'll get a test made out. I've not had exactly this combination before, so I've got to make out a new test, but I've had questions from both, so I think I can do it fairly quickly and get this done. I might even get my work study student on it, except he's not here today. Hopefully if he's here tomorrow, he can do some of that while I'm teaching my class in the afternoon. So we'll pick up and go from there. As soon as we finish 11.2, we'll pick up in chapter 12. And we'll do most of chapter 12. Maybe not all of it, but most of 12. Good deal. We'll see you Wednesday.
Do we have to do the research paper for Math 238?
Yeah, there's one for each. Yeah, always.
Because I missed the,
Yeah, you missed it very
days.
first. Yeah.
Very first days.
Yeah. Well, if you check Blackboard, it's all out there. The instructions are there. They're just like the instructions for this one, but also the first day of class, the first 2 days of class, I go through all that stuff.
Okay, so we have to pick a topic from the...
Yeah, anything. Yeah, like 238. Yeah.
I'll see you later.
All righty.